Good afternoon, everyone. It's a pleasure for me to introduce the lecture of Professor Alberto Elduque. He will continue his course on composition algebras. So please, Professor.
Okay, thank you very much. Remember what we have been doing so far. The first day we considered the classical real division algebras of real complex numbers, Hamilton quaternions and octonions. And then we started to study those algebras that generalize all these algebras. And these are the unital composition algebras. So we substitute the usual Euclidean norm by non-degenerate, or better, non-singular quadratic form, which is multiplicative, and this was the crucial point for the classical algebras. We check that all these algebras have dimension 1, 2, 4, or 8 and are constructed or described in the same way as the classical ones. And in particular, we studied those that have isotropic norm. I mean that there are non-zero elements whose norm is 0, because this is what happens over algebraically closed fields. And in that situation, we know that we have some uniqueness up to isomorphism. There is a unique algebra in dimension 2, another unique algebra in dimension 4, which is just the algebra of 2 by 2 matrices with the determinant as norm, and the split Cayley algebra. And we consider several properties of these algebras. And finally, we went to symmetric composition algebras, and these are composition algebras which are not unital, but the norm has this nice property, which is the property of being Frobenius in Justin McEnroy's course, which is just that they satisfy this property, this nice property. The polar form of the norm is associative relative to the product. And now, since we are dealing with several products at the same time, I always specify the notation for the product and the notation for the norm in all cases. So we were dealing with these symmetric composition algebras, and we look at examples. We had a characterization, and the first example is the so-called para-Hurwitz algebras. By the way, these algebras have appeared this morning in the talk by Professor Guterman. It's one of the families of standard composition algebras. So para-Hurwitz algebras are just Hurwitz algebras where we modify the product. We consider a new product, and instead of multiplying two elements x, y in the Hurwitz algebra, we multiply the conjugate elements x bar and y bar by the canonical involution that we have. This was our first example, and we checked that this is symmetric composition algebra. And then we consider another interesting example that comes from an associative algebra. So we take zero trace 3 by 3 matrices over a field containing a primitive cubic root of 1. This imposes that the characteristic, this forces that the characteristic is different from 3. And in this 8-dimensional subspace of zero trace matrices, we define a product by multiplying the matrices xy, then multiply yx, taking a suitable linear combination, and then adjusting to get a zero trace matrix. And with natural norm that appears defined in this 8-dimensional space, we get another example of symmetric composition. Actually, this can be done for any central simple associative algebra of degree 3 over fields that contain primitive cubic roots of unity. And in case we don't have a primitive cubic roots of unity, we have to get to the corresponding degree 2 field extension, adding this primitive cubic root of unity, taking matrices, or more generally central simple associative algebras of degree 3 over this field extension, but with an involution of the second kind, like the usual unitary involution for 3 by 3 complex matrices. And one uses the same definition of multiplication and norm, but this time on the set of zero trace matrices or elements that are also askew with respect to the involution of the second kind. And these were our examples of Okubo algebras, and in particular of symmetric composition algebras. Okay, so one interesting thing is that given one of these Okubo algebras constructed in terms of matrices or more general central simple associative algebras of degree 3, we can recover from the product in the Okubo algebra, from the star product, if you take two elements and multiply x times y and y times x, and play a little bit with a suitable linear combination of it, it turns out that we can recover the matrix product in terms of the Okubo product. We can recover the usual product of matrices x, y in terms of the Okubo product and the norm in the Okubo algebra. Okay, so this is quite interesting. And actually, Faulkner realized that this construction is valid not just for 3x3 matrices or central simple associative algebras of degree 3, but also for separable alternative algebras of degree 3. Okay, so and this was a key point to get a nice classification of the symmetric composition algebras over fields of characteristic different from 3. And this is how it works. So if we start with a field of characteristic not 3, we have two possibilities. If F contains a primitive cubic root of 1, then the symmetric composition algebras, well, in dimension 1, only symmetric composition algebra is the ground field, so there is nothing to look at, so we will consider dimension at least 2. So the symmetric composition algebras of dimension at least 2 are up to isomorphism, the algebras that can be obtained with Okubo's multiplication and norm, but starting not with a central simple associative algebra of degree 3, but starting with any separable alternative algebra of degree 3. And actually, two such symmetric composition algebras are isomorphic if and only if so are the corresponding alternative algebras. So over this kind of fields, the twisting of the multiplication of matrices or more generally on any separable alternative algebra of degree 3, this twisting given by Okubo gives all the possibilities. And the corresponding symmetric, including the para-Hurwitz examples. I will come back to this in a minute. So all the examples that we have are included here. And actually, all symmetric composition algebras are obtained in this way. And two such symmetric composition algebras are isomorphic if and only if the alternative algebras are isomorphic. Since separable alternative algebras are well known, this gives a complete classification. And in case the ground field of characteristic different from 3 doesn't contain the primitive cubic roots of 1, then we have to do exactly the same thing that the Okubo did. Extend to a degree 2 extension, adding the primitive cubic root of 1, considering a separable alternative algebra of degree 3 over the field extension with an involution of second kind. And now we take the subspace, the 8-dimensional subspace of 0 trace elements that are skew relative to the involution with the star multiplication and the norm given by Okubo with the same formulas that Okubo used. And in this way, one gets all symmetric composition algebras over this kind of fields. And again, two symmetric composition algebras are isomorphic if and only if the corresponding alternative algebras are isomorphic as algebras with involution. Okay, so we must take into account the second kind involution. And this gives a complete classification. Actually, a complete classification was given for fields of characteristic not 2 or 3 2 years earlier, using the fact that symmetric composition algebras are Lie admissible and using some properties of Lie admissible algebras. But with Faulkner's idea that one can substitute central simple associative algebras of degree 3 by alternative algebras and apply the same construction, things became easier to deal with. Okay. So how this is proved? Well, essentially, one has to make the computation that we already considered yesterday. And this computation can be also go in the reverse direction. Okay, so if we start with a symmetric composition algebra, and if the field is good enough to contain the primitive cubic roots of 1, say omega, one of these cubic roots of 1, then one can define a new algebra adding a unity. So we get dimension 9. And then remember that the multiplication, the matrix multiplication can be recovered from the Okubo multiplication. Well, now we can use the same formulas to define a product in A. And now it's relatively straightforward to check that the multiplication that one gets in A makes A separable alternative algebra of degree 3. It may fail to be associative. And actually, this happens, it fails to be associative if the symmetric composition algebra that we start with is para-Hurwitz, actually para-Cayley in dimension 8. This is the only case where this may fail to be associative. If the field doesn't contain the primitive cubic roots of 1, then one has to extend scalars and do exactly the same thing, extending scalars. So the idea is that from any central separable alternative algebra of degree 3, considering the same formulas that Okubo considered, one gets a symmetric composition algebra, and one can go in the reverse direction from any symmetric composition algebra, adding a unity and defining a product using the formulas that we have already considered. One can recover an alternative algebra of degree 3, separable alternative algebra of degree 3. So that's it. This is the idea of the proof, that we can move from these alternative algebras to symmetric composition algebras, but we can also go back, and this gives the result. So things are not that difficult. Okay. So as a corollary, we get that the examples that we have of symmetric composition algebras, so we have the para-Hurwitz algebras and the Okubo algebras. Well, this essentially exhausts all symmetric composition algebras over fields of characteristic not 3. And why is so? Well, if F contains a primitive cubic root of 1, we consider the field F. If not, we extend the field by adjoining a primitive cubic root of 1, and we get a Galois field extension of degree 2. So K is will denote this field. And then what we have to do is to check at the different possibilities of separable alternative algebras of degree 3. And the separable alternative algebras of degree 3 are either central simple associative, and if they are central simple associative algebras, what we get are the Okubo algebras using Okubo's cosine. So this is the first possibility. The second possibility is that our algebra is up to isomorphism, a Cartesian product of the field, which is F or K, depending, and a degree 2 separable alternative algebra. But a degree 2 separable alternative algebra is just a Hurwitz algebra. These are the only possibilities for this. So the second possibility of a separable alternative algebra of degree 3 is a Cartesian product of the field and a Hurwitz algebra. And if this is the case, using Okubo's formulas, what we get is the corresponding para-Hurwitz algebra attached to C. Well, not exactly to C, because to C if the field is F, if the field contains the primitive cubic roots of 1. If not, well, we have C hat, which is a unital composition algebra over F, and this is the para-Hurwitz algebra we get. So either we have a central simple associative algebra of degree 3, and then what we get are exactly the Okubo algebras, or we have a Cartesian product like this, and then we get a para-Hurwitz algebra, or what we get comes from a cubic field extension of L. And then in this case, what we get is a two-dimensional, using Okubo's formulas for the product and the norm, we get a two-dimensional symmetric composition algebra, which is not para-Hurwitz, but it becomes parahurvis after a field extension. So essentially, these are parahurvis. That's why I wrote essentially exhaust parahurvis and Okubo algebras, essentially exhaust, because what we get is that either we get Okubo algebras, or we get parahurvis algebras, or we get forms, twisted forms of parahurvis algebras in dimension 2. That's it, in dimension 3. Now, the natural question is, and characteristic 3? Well, it's clear that in characteristic 3, there are no primitive cubic roots of 1, because the equation x cubed equals 1 has a unique root. This is equivalent to x minus 1 cubed equals 0. So the only cubic root of unity is 1 in a field of characteristic 3. So nothing of what we have talked about previously works in characteristic 3. We don't have these omegas that allows us to twist the multiplication in matrix algebras. So nothing of this type works. So what can be done? And the clue to deal with characteristic 3 was a result by Peterson, valid in characteristic different from 2 and 3. So the clue was given by a result that works only in characteristic different from 3, but it gave the clue to deal with characteristics. And this is the result by Peterson. It was not a result about composition algebras. It was a result about flexible algebras. Algebras that satisfy this property are called flexible, plus an extra equation, an extra identity. Okay? And Peterson, studying some classes of flexible algebras, considered this class of algebras. And well, this identity is natural if one thinks about the quadratic operation that appears in Jordan algebras. So I guess that was the motivation behind this result. And what Peterson proved is that if we are dealing with an algebraically closed field in characteristic different from 2 and 3, otherwise this is not true, then the only simple finite dimensional algebra satisfying these two identities are parahurvis or another algebra. And this unique other algebra is constructed starting with the split-Cayley algebra by modifying the multiplication, and modifying the multiplication again with x bar and y bar, but there is an extra twisting by an oromorphism phi of order 3. And this is precisely the oromorphism given by Peterson. Remember that the split-Cayley algebra, in split-Cayley algebra, we may find easily idempotents, orthogonal idempotents, E1, E2. So these are fixed by phi. And then we have the pairs decomposition. And in the pairs decomposition, there appear two three-dimensional pairs components that we call U and V. So the whole algebra splits as, well, the multiples of one of the idempotents, the scalar multiples of the other idempotent, and then two three-dimensional vector spaces, U and V, okay? And so in these three-dimensional vector spaces, we took dual bases, U1, U2, U3 for U, and the dual basis relative to the norm in V, because these space components are isotropic. So what Peterson got was that there was a unique other algebra, and this unique other algebra can be described by twisting, deforming the multiplication, the split-Cayley algebra, not just taking the conjugates, as in the parahurvis case, but taking the conjugates and applying a particular oromorphism of order 3 obtained in terms of a primitive cubic root of 1. So that's why he needed characteristic different from 3, and besides, in some of the arguments, he needed characteristic different from 2 also. But see, he was dealing with an algebraically closed field and studying algebras that satisfy these properties. Well, any symmetric composition algebra satisfies this property. Because remember, in any symmetric composition algebra, these two things are equal and are equal to the norm of x times y. So actually, what we get here is a scalar multiple of y. So any symmetric composition algebra satisfies this thing. But any symmetric composition algebra also satisfies this other identity. Because here we get a scalar multiple of y given by the norm of x times z. And the same happens here because of the multiplicative property of the norm. So any symmetric composition algebra over an algebraically closed field of characteristic different from 2 and 3 must appear here. And it turns out that if the field is algebraically closed field of characteristic different from 2 and 3, the previous theorem gives us only two possibilities: Para-Hurwitz or Okubo. The Okubo algebra obtained from 3 by 3 matrices over the field, the original algebra of pseudo-octonions given by Okubo. Okay, so the outcome is that this algebra here in the second item of the theorem must be the algebra obtained by Okubo over an algebraic closed field. So although this theorem is much previous to the work of Okubo, and it's not a theorem about composition algebras, but then with hindsight, after all the work by Okubo, Osborne, and other people, this had to be the Okubo algebra. So actually, this is the first appearance of Okubo algebras in the literature, but in characteristic different from 2 and 3, and only for algebraically closed fields. Okay, so this is the remark I've just done. Over these fields, algebraically closed field of characteristic different from 2 and 3, the last algebra in Peterson's theorem must be the algebra obtained from 3 by 3 matrices over the field using Okubo's construction. Okay. So this gives an idea. A light turn on. So see, take any Hurwitz algebra. Take any holomorphism of order 1 or 3, and then twist the multiplication in the Hurwitz algebra using the conjugation and this holomorphism. And we decided to give these algebras the name of Peterson algebras. Okay, so instead of just twisting to get para-Hurwitz algebras, we decide also to twist with an holomorphism. Well, Peterson considered a specific holomorphism given in terms of cubic root of unity. But we can consider other holomorphisms of order 3, and it turns out that everything works. These are symmetric composition algebras. And see, in case the holomorphism is the identity, what we get is just the para-Hurwitz multiplication, x bar times y bar. Okay, so it includes para-Hurwitz algebras. Peterson algebras include para-Hurwitz algebras. But see, we can consider, Peterson considered a very specific holomorphism using the primitive cubic root of unity and so on. But see, in the split Cayley algebra, there is another natural holomorphism that works over any field. We can fix our orthogonal idempotents. And now we have these two three-dimensional vector spaces. Okay, in these three-dimensional spaces, we have a basis in U and the dual basis in V. Okay, we can permute cyclically these bases, both in U and V. And this is clearly an holomorphism because the multiplication, the split Cayley algebra, doesn't depend on the particular order of the elements of the basis. But we have to keep this alternating trilinear form that I considered yesterday. One has to keep some properties here. But if you permute cyclically the elements in both the basic elements in both U and V, everything is preserved. So in particular, this is an holomorphism. And it's clear that it is an holomorphism of orders. So in the split Okubo algebra, we consider the order 3 homomorphism that fixes the idempotence and permutes cyclically U1, U2, U3. And well, now we can use this holomorphism to consider the corresponding Peterson algebra, and this gives a symmetric composition algebra which is valid in any characteristic, because we don't need cubic roots of unity here. This works in any characteristic. So this allows us to give a definition of Okubo algebras independent of the characteristic. Okay, because up to now, the definition I had given you depended on the characteristic being different from 3, and it was different depending on the field containing the cubic roots of unity or not. So now here is a definition valid in any characteristic. First, we define the split Okubo algebra as the algebra that we have just constructed. So we take the split Hurwitz algebra and modify the product. We deform the product using conjugation and this particular holomorphism of order 3 that works in any characteristic. So this will be called the split Okubo algebra. And now the twisted forms of the split Okubo algebra, I mean, the algebras that become isomorphic to the split Okubo algebra after extending scalars to the algebraic closure of the field, these are called Okubo algebras. And this is a new definition that was given almost 20 years after the discovery by Okubo of these algebras. But the nice thing about this definition is that it works in any characteristic. And actually, the algebras that one obtains in characteristic different from 3 are exactly the algebras that we obtained before. Because any of the algebras that we obtain over fields of characteristic different from 3, both in case that omega belongs to F or in case omega doesn't belong to F, after extending scalars, become the split Okubo algebra, isomorphic to the split Okubo algebra. Okay. So this is the new definition. And well, this is the multiplication table of the split Okubo algebra using the same basis, although I have reordered things. So here I have U1, U2, U3, and I have reordered these things because in the split Okubo algebra, we have a subalgebra spanned by the idempotence, but we have an isomorphic algebra, subalgebra, spanned by U1 and V1, and another isomorphic algebra spanned by U2, V2, and another isomorphic algebra spanned by U3 and V3. So the split Okubo algebra is the direct sum of 4 isomorphic two-dimensional algebras, which by the way are para-Hurwitz in dimension 2. And then we mix all the 4 para-Hurwitz subalgebras to get the whole multiplication. Okay, so this is the split Okubo algebra. Okay, some remarks. Well, the first has already been explained. The new definition coincides with the old definition in characteristic different from 3. Actually, it is simpler because we don't have to split our situation depending on whether the field contains the cubic roots of unity or not. So this is a nice general definition of Okubo algebras. And using the multiplication table of the split Okubo algebra, one can check immediately that the commutative centers, I mean the set of elements that commute with any other element, is 0 in the split Okubo algebra. However, in para-Hurwitz algebras, we always have elements that commute with all other elements. The commutative center is always different from 0 because the para-unit commutes with everything. The unity of the Hurwitz algebra becomes the para-unit in the para-Hurwitz algebra, and this commutes with everything. So Okubo algebras and para-Hurwitz algebras always form disjoint families. In Okubo algebras, the commutative center is always trivial. In para-Hurwitz algebras, it's never trivial. Okay. Now, there is still the problem of Okay, but we know the classification of symmetric composition algebras over fields of characteristic different from 3. Because essentially it goes to the classification of certain alternative algebras over these fields, and we know this classification. Unfortunately, in characteristic 3, symmetric composition algebras are not related to alternative algebras of degree 3. So we cannot use the same ideas to classify symmetric composition algebras in characteristic 3. However, starting with the split of cubo algebra over a field of characteristic 3 and taking the algebraic closure, well, the split of cubo algebra is defined on the vector space, which is the same vector space as the split Cayley algebra. So just extend scalars to the algebraic closure. Take any two different elements in the field. And in this tensor product, consider the elements E1, the first orthogonal idempotent of the Cayley algebra, tensor with the cubic root of alpha, and then take U1 tensor with the cubic root of beta in F bar. These cubic roots are unique, so this is well defined. Okay, and now take all the elements that are obtained by multiplying these two things, and then multiplying with the gets you obtain, and so on, and taking linear combinations with coefficients in F, not in F bar, in F. Okay, and if you do that, you just multiply and take linear combinations over F. What we get is a twisted form of the split of cubo algebra. So an algebra that becomes isomorphic to the split of cubo algebra after extending scalars. This is clear from the construction, but that depends on two parameters, alpha and beta, two scalars. Denote this algebra in this way, O sub alpha and beta. And this is a twisted form of the split of cubo algebra. So this is an cubo algebra. Well, the interesting thing is that in this way we get all the cubo algebras. So what is the classification of symmetric composition algebras over fields of characteristic 3? Well, it is different from, certainly different from the classification in characteristic different from 3. But anyway, either we get a paracurvis algebra, exactly as in other characteristics, or some two-dimensional algebras that are not paracurvis, but become paracurvis after scalar extension. So they are forms of paracurvis algebras. So up to now, this is essentially the same thing that happened in other characteristics. Now, in characteristic different from 3, what is left are the cubo algebras, and the cubo algebras are related to central simple associative algebras of degree 3 in characteristic different from 3. In characteristic 3, this is the difference. The remaining possibility is that either we have paracurvis or a two-dimensional form of paracurvis, or we get an algebra isomorphic to one of these algebras that we mentioned before. And these algebras have no close connection with matrices. Okay, so they are defined in terms of the split of cubo. Depends on two parameters, and we know the conditions for isomorphism. I'm giving you here the condition for being isomorphic or anti-isomorphic, and it depends on the elements alpha, beta on one side, and the elements gamma and delta on the other side. Okay, this is a technical condition. On a first reading, one can forget about these kind of things. The message is that the classification characteristic 3 is different. And it's different, and the kind of algebras that appear are different. The forms of the split of cubo algebras are obtained in a different way. Okay, actually, we know precise conditions for isomorphism, so I can add some extra conditions here and forget about anti-isomorphism here, but this is too technical. We will forget about that. And the question is that, I guess this is going to be one of the messages that you are going to get from all these courses, is that idempotents are important. This is clear in in the course on axial algebras by Justin McEnroe. Actually, these algebras contain the axes and are called axial algebras, and all the axes are idempotent. And the study of these algebras depends on how these idempotents behave and relate. Well, here, idempotents are also very important. As soon as an Okubo algebra contains an idempotent, what we get is a Peterson algebra. So starting from this idempotent, we can move to a Hurwitz algebra together with an oromorphism of order 3. And then we can classify oromorphism of order 3 and get the result. The difficult part is whenever there are no idempotents, and this happens, there are examples with no idempotents, and this was the most difficult case to prove, to see that Okubo algebras in characteristic 3 without idempotents belong also to this family I mentioned, this O alpha beta. Okay, so this is the way to proceed. Okay, and let me finish with triality. Now I'm not going to give many details, although I will put these slides on my webpage, so you will be able to see more details there. What is triality? The triality phenomenon. This is a very interesting phenomenon. And it is related to the Dinking diagram D4 that has a central vertex and then 3 other vertices. And among Dinking diagrams, this is the most symmetric. This symmetry group of this Dinking diagram is the symmetric group of degree 3. For all the other Dinking diagrams, at least corresponding to split simple algebras, either the symmetry is trivial, there are no symmetries, or the symmetry group is the cyclic group of order 2. So only for D4 we have extra symmetries. In particular, we have a cyclic symmetry that permutes the outer vertices of the diagram. So triality is related to this extra symmetry that appears in dimension 8 related to D4, I mean related to quadratic forms in dimension 8, some quadratic forms in dimension 8. And the nicer way to deal with this triality phenomenon is using symmetric composition algebras, because from the geometric point of view, there is an old beautiful paper by Titz dealing with the geometric triality, and there it appears clearly that there are 2 types of geometric triality. One type related to the exceptional Lie group G2, and another type related to the exceptional Lie group A2, type A2, in characteristic different from 3. If the characteristic is 3, the group that appears is not A2. Still, we have a triality related to G2, and another one related to an 8-dimensional subgroup of G2. So there was something strange in characteristic 3 that was already discovered from a geometric point of view. So if we start with an 8-dimensional symmetric composition algebra, so either para Hurwitz or Okubo in dimension 8, there are no other possibilities, with multiplication denoted by the star, consider the left and right multiplication by an element x. And see, the definition of, well, not the definition, but the first property that we look about symmetric composition algebra is exactly this, that if we take an element y and we multiply this element y by x on the left and then on the right, or it doesn't matter whether we do first on the left and then on the right or the reverse way, we always get a scalar multiple of y, and the scalar is given by the norm of x. So this was the first property we look at for symmetric composition algebra. So now consider 2x2 matrices over the endomorphism algebra of S, of this 8-dimensional vector space. Okay, and consider this specific matrix: 0 in the 1,1 slot, 0 in the 2,2 slot, and then the left multiplication by x, which is an endomorphism of S, and the right multiplication by x, on the off-diagonal slots. Well, if you take the square of this matrix, what you get is, using this property, what you get is a scalar multiple of the identity matrix with the norm as the scalars. So this allows us to consider the map that takes any element in the symmetric composition algebra to this 2x2 matrix. And because of the previous property, this allows you to extend this map to a map from the Clifford algebra of the norm to this algebra of matrices, of 2x2 matrices. If you are not familiar with the Clifford algebra, don't worry. The Clifford algebra is an associative algebra attached to any vector space with a quadratic form. And this is a very important invariant of the quadratic form. The well-known spin groups that are used by the physicists all the time are defined in terms of this Clifford algebra. And many other properties of the quadratic form are. So this is a very important invariant attached to the norm of the symmetric composition algebra. And all this allows us to give an isomorphism between this Clifford algebra, which is so important to define spin groups and so on, and representations of the corresponding groups, with an algebra of 2x2 matrices over endomorphisms of S. Okay, so well, I'm not going to go into details. This isomorphism also is an isomorphism of algebras with involution, where in the Clifford algebra side we consider the standard involution, the canonical involution on the Clifford algebra, and on the right side we have the involution given by the norm on each copy of the symmetric composition. So, well, since here we are dealing with many different products, the product in the symmetric composition algebra is denoted with a star, and the product in the Clifford algebra with a dot. Okay? And with this, we can consider the spin group. Here you have the definition. The spin group consists of the elements in the even part of the Clifford algebra, which are invertible, preserve the S, the subspace S, which is inside the Clifford algebra, and satisfy that the spinor norm is 1. This is the canonical involution of the Clifford algebra. Well, the spin group is defined inside the Clifford algebra. And what happens is that this isomorphism from the Clifford algebra into the algebra of 2x2 matrices takes any element in the spin group to a diagonal element where the endomorphisms that appear in the diagonal part are precisely the half spin representations of the spin group. These are very important representations. What happens in dimension 8 is that the natural and spin representations, the three of them have dimension 8. And moreover, what happens is that using the multiplication in the symmetric composition algebra, we have that the two half-spin representations and the natural representation of the spin group, the natural representation is just by conjugation inside the Clifford algebra. The three natural and important, the three most important representations of the spin groups are related using the multiplication in the symmetric composition algebra. Moreover, here we can permute cyclically the three representations. Okay, so this formula here links the natural and the two half-spin representations of the spin group. And this is what reality is about, that this outer oromorphism of the Dynkin diagram allows us to permute these three eight-dimensional representations. Okay. Well, this can be considered in a different way. I'm going to skip this thing. But the important thing also is that in this way, we can identify the spin group associated to the norm of any symmetric composition algebra we can identify this spin group, which is the universal cover of the special orthogonal group, in exactly the same way as we considered in the first talk, the first day. Remember that the three-dimensional sphere was the universal cover of the special orthogonal group of degree 3 over the real numbers. Well, the S3 is the spin group in that case, okay? But this can be done in much more generality over arbitrary fields and so on. So what happens is that the spin group, which is some universal cover of the special orthogonal group, is isomorphic to a group of triples of a special orthogonal transformation related by this condition, which is the same condition that appeared before. Okay, and the projection, the natural projection of the spin group on the special orthogonal group is just the projection onto the first component. So we have a very clear description of the spin group in terms of orthogonal transformation. And we have cyclic symmetry, and this gives the triality oromorphism, and so on. So message, symmetric composition algebras are quite important to study spin groups in dimension 8 and the phenomenon of triality in dimension 8. Okay, this is, well, since I don't have much time, what happens is that we have the oromorphism, the natural oromorphism that permutes cyclically these three elements. And this is an outer oromorphism of order 3. And the fixed subgroup, it is a subgroup here. The fixed subgroup coincides, well, the fixed sub, if we permute cyclical and we consider the fixed elements are the elements where F1 equals F2 equals F0. So the fixed elements are the oromorphisms of the symmetric composition algebra. And that's why there appear two kinds of possible trialities, depending on the symmetric composition algebra being para-Cayley, para-Hurwitz, or Okubo. If it is para-Cayley, this oromorphism group is of type G2. If it is Okubo, it's of type A2. Okay. So, well, type A2 if the characteristic is different from 3. Okay. So, with any symmetric composition algebras, we can use the symmetric composition algebra to define a very nice isomorphism from the corresponding Clifford algebra into a very concrete algebra. Algebra of 2 by 2 matrices over the algebra of endomorphisms of this 8-dimensional space. And using this isomorphism, we can deal in a very nice way with the phenomenon of triality in dimension 8. What happens in characteristic 3? Because I told you, well, if the characteristic is different from 3, we have something of type A2. What happens in characteristic 3, and this was proved a few years ago in collaboration with Tignol, Chernusov, and Nuss, that the group scheme of oromorphisms of an Okubo algebra with a field of characteristic 3 is not smooth. As a group scheme, not as a group, this is not smooth. The smooth part, the reduced part, has dimension 8, and it is as a group that lives inside the exceptional group of type G2. And this is what Tits realized that happened dealing with reality in a geometric way, with points and solids and interchanging these types of things. So he realized that characteristic 3 was different, and what he got had nothing to do with A2. And well, since he was just dealing with the rational points, he got a group of dimension 8, which is not simple. It has a large unipotent radical, and there are plenty of properties that come from this. Okay. And well, all this can be done considering Lie algebras instead of groups. So considering Lie algebras, the natural Lie algebra that appears here is the orthogonal Lie algebra, which is here. And well, since I'm running out of time, one can consider also related triples of not of orthogonal transformation, but of elements in the corresponding Lie algebra with the local version of what we have done so far. And so we can talk about the triality Lie algebra, which is this algebra. And here things are easier. This is isomorphic to the orthogonal Lie algebra. So this is easy, but this gives a nice interpretation of the outer holomorphisms of order 3 in the orthogonal Lie algebra in dimension 8 because of the symmetry of the linking diagram. So there is a natural cyclic holomorphism. We permute cyclically the elements in these triples. And let me just get past this and go to this nice construction of the so-called Freudenthal magic square. Well, Freudenthal constructed this square in the 50s using each row of the square corresponded to a different symmetry. The last two to symplectic and metasymplectic geometry, the last row corresponding to a new kind of geometry. So it was elliptic, projective, symplectic, and metasymplectic geometry. But in terms of algebras, see, if we start with two symmetric composition algebras, S and S prime, we can define a Lie algebra on this direction. We take the triality Lie algebra of S, the triality Lie algebra of S prime, and then 3 copies of the tensor product of S and S prime. Okay. Now, we can define a Lie bracket here. How? Well, in the triality Lie algebras, these are already Lie algebras. So they already have a Lie bracket. We preserve this Lie bracket. Now, the action of any related triple on an element of this form, well, if we have the index 1 here, it is the one that applies. Okay, so the corresponding term in the triple is the one that applies. Same in the second component. And then we have to define the brackets. So if we want to define the bracket of iota 1 with iota 2, then it goes to iota 3. And what we do is just we multiply x times y in the first symmetric composition algebra and x prime times y prime in the second symmetric composition algebra. So the natural product. And well, I haven't defined these elements, but these are natural elements and the natural triality holomorphism, but it can be defined, the bracket. Let's say in a natural way, whenever the two indices are equal here. Okay, so we have a vector space defined in terms of two symmetric composition algebras, considering 3 copies of the tensor product plus the corresponding triality algebras. One defines the product in this way, the Lie bracket, and the kind of algebras that appear are always simple or almost simple, and we get all the exceptional, with the exception of G2, simple Lie algebras, classical simple Lie algebras, the F4, E6, E7, and E8. So in a unified way, we define all these exceptional simple Lie algebras. Okay, I put characteristic different from 2 and 3. Characteristic 2 is different in this construction, and characteristic 3 works well with the exception of the second row and second column. For instance, here, in the split case, we don't get 0 trace matrices of size 6. But we get, so instead of the special linear Lie algebra, we get the projective general linear Lie algebra. which is not simple. Okay, so one has to be a bit careful in characteristic 3 with the second row and second column. But apart from that, characteristic 3 works in the same way. And this is a beautiful unified construction of the exceptional simple algebras. Actually, different versions of this square have been constructed over the years. Many of these constructions using Hurwitz algebras. But the formulas for the Lie bracket are simpler if one uses symmetric composition algebras. So this is one interesting thing about using symmetric composition algebras. The other interesting thing is that there are two types of triality, and depending on which symmetric composition algebra, whether you use para-Hurwitz or Okubo algebras, it's easier to deal with with the corresponding type of triality or homomorphism. Okay, so the formulas that one gets are simpler using symmetric composition algebras. Also, depending on which symmetric composition algebra you use, this is reflected in some kind of symmetries that appear naturally in these algebras. So, for instance, you can get E8 using the two symmetric composition algebras para-Hurwitz algebras, the two Okubos, or one para-Hurwitz or one Okubo. And depending how you construct this largest Lie algebra E8, depending on which construction you use, you get different symmetries. Some symmetries of the algebra come out more easily. Okay? And also very interesting is that in characteristic 3, and only in characteristic 3, there are composition superalgebras. And all these can be dealt with for superalgebras. One can consider triality superalgebras and all these kind of things that we have considered so far. So this construction can be used with these superalgebras that exist, composition superalgebras and symmetric composition superalgebras that exist only in characteristic 3. And this has allowed us to discover new simple Lie, finite dimensional simple Lie superalgebras in characteristic 3. And this has been a quite nice outcome of all this. Okay, I have run out of time several minutes ago. Well, I wrote a survey paper on these things in a kind of encyclopedia edited by Professor McClough, who will talk now. So the second chapter in this encyclopedia is about composition algebras. So you can find a survey of all these things, and there you get references to all the things I've talked about. And anyway, this is freely available on the archive or on my webpage. And well, that's all I wanted to say. Thank you indeed very much for your attention.
Thank you, Professor Elduque. Well, if there are any questions, maybe we will start some discussion. We have some time. Well, there are two. Okay, we have two questions. Svetlana, you may speak.
Professor Elduque, Okubo algebras with idempotence are Peterson algebras, so we know the explicit multiplication tables.
Yeah.
But are there any multiplication tables which are readable, at least for Okubo algebras without idempotence?
See, in characteristic 3, these are the algebras O alpha comma beta. Okay, and the multiplication table appears in some of my papers. I can send you the exact references. But even if, so, in a way, this case of characteristic 3 is simple. But in characteristic different from 3, also what happens is that Okubo algebras have a grading by 2 copies of the integers modulo 3. And using this grading, one gets a nice multiplication table. that depends on alpha and beta, and it is exactly as in this case of characteristic 3. So I have a paper on gradings on symmetric composition algebras, and there you may find this grading and the multiplication table.
Okay, thank you. Thank
You're
you.
welcome.
And another question, I guess it's from Madagascar.
By the way,
Yes.
sorry, just to
So,
finish this. Excuse me one moment. This grading by 2 copies of the integers modulo 3 was the key point to check that in characteristic 3, the oromorphism group of the cubo algebra is not smooth. So this grading has became very important.
Thank you.
Not just for the multiplication table, it became really important in characteristic 3. Yes, sorry.
Okay, and another question from Madagascar. You may share your video and microphone to ask a question.
You must unmute your microphone.
Really?
Yes, okay.
Okay, Professor, do you hear me?
Yes.
Yeah. In the 67th page, you say that a group scheme of automorphism of an occupable algebra of a field of characteristic 3 is not smooth. So what do you mean about smooth there? Because I think like a smooth in the topology. And
yeah. Yeah. In characteristic 3, we don't have the usual topology, but we can think of the oromorphism group as an algebraic group. And by this, I mean that we have all algebraic geometry that we can use. And it is in the sense of algebraic geometry. So the topology that we are using is Zariski topology. And this is what happens. Yes. So.
Oh, okay. Thank you very much.
So one can talk about many results about Lie groups. This is quite interesting. Many results about Lie groups over the real numbers or complex numbers can be extended to groups over arbitrary fields. But of course, there we don't have differentiable manifolds or things like that. We don't have the usual topologies. But still, algebraic geometry is there, and we can use algebraic geometry. And when we look at the oromorphism group as an algebraic group in the sense of algebraic geometry, and especially as a group scheme, so-called affine group scheme, this is where there is a natural notion of smoothness, and this is and only in characteristic 3, the oromorphism group of cubo algebras are not smooth, only in characteristic 3.
Okay, if there is no question, let us speak. Let us thank Alberto once more.
Thank you. There seems to be another question.
Another question appeared, yes.
It's not a question, but a comment. So when the student, the participant from Madagascar, saw your talk, so their comments is your talk is very high level and very clear. So thank you very much.
Thank you very much for your attention. It was a real pleasure to give this course. Thank you.
I saw there was one more question from John Alexander Ramirez Bermudez. Do you want to ask a question? Or it was just by mistake that you have raised in your head?
No, sorry, no.
Okay.
Just for give the thank you to Alberto for the course. Was a fantastic course, and I learned a lot of that course. Thank you, Alberto.
Oh, thank you.
May I ask you? May I ask just one question? This is Sergei Silvestro from Sweden. Is calling.
Hi, Sergei.
Hi, Alberto. First, thank you for your lectures. It was very interesting for me to listen it, especially because I read your book with Jung about other things, mutations and some other things. But I have just a general mathematical question to your lectures. As I understand, for all of these results, multiplicativity of the norm is essential, so to say. I mean what you call a norm, so to say.
Yes.
So it is actually kind of mimicking a degree situation for polynomials, but usually in norm is submultiplicative in sense of Banach algebras and sense of normed algebras and so on. So my question is more general. How many of those no-go results, so to say, so results which would say that only algebras appearing with that and that property, say Hurwitz algebras or some other this type of algebras are in this and that dimension, which is just let's say no-go theorems, which says that it doesn't exist in other dimensions. How much it depends on just this very strict multiplicativity property, so homomorphism property of the n.
It depends quite a lot of the multiplicative property. For instance, with the Cayley-Dixon doubling process, one can get higher dimensional algebras where the norm is not multiplicative, although it has some properties. But these algebras are quite interesting to study some things like the zero divisors, and they constitute nice sets with but these algebras are more rigid. The important part is that they are less symmetric than the algebra. So we have very nice algebras up to dimension 8 with very interesting symmetry groups like G2, A2, or things like that. Orthogonal groups are acting there too, spin groups are acting there. And then when we move further, this symmetry is lost. These large symmetry groups are lost. But still, there is room to study the algebras that appear. And I'm pretty sure that over the real numbers or complex numbers, as you mentioned, if instead of the multiplicative property, one uses some sub-multiplicative properties, I'm pretty sure that many interesting results may be obtained. Yes. But the nice thing about these low-dimensional algebras is that they are very symmetric, therefore very beautiful.
Yes.
Let's see. And they are related to the exceptional groups, and this is quite important.
Yes. Okay, thank you very much for your course, and it was very interesting to listen. Yeah, thanks.
Thank you, Sergei.
Okay, thank you, Professor Alberto. Thank you.